How do you take images so fast that you can see light traveling through air? How do you take pictures without using a camera? And how do you use the latest technology to look around corners and see objects hidden from view? These are the questions that researchers from Heriot-Watt University and the University of Glasgow, the Creative Cameras team, are looking into. Light is made up of photons travelling at 300 million meters per second, and nothing can travel faster than the speed of light. Photons travel so fast that normal cameras cannot freeze their motion as they move. But the team at Heriot-Watt University is using a new type of camera, a camera so sensitive and so fast that we can capture individual photons and take videos of pulses of light as they travel through air. The camera, developed by the University of Edinburgh, is made up of an array of single photon sensitive pixels, and these pixels have two very special properties. The first is their sensitivity to single photons. Each pixel is around 10 times more sensitive than a human eye. The second is their speed. Each pixel can be activated for just 67 picoseconds. That's more than 1 billion times faster than your eye can blink. These properties allow us to perform light-in-flight imaging, an approach to imaging where light itself is captured as it travels through air and scatters off objects. The camera works in combination with a pulsed laser source. Photons in the pulse of light travel through air. Here, we see them reflecting off a series of mirrors. The pulses randomly scatter individual photons when colliding with air molecules. Some of these photons are captured by the camera. When the pulse of light leaves the laser, a signal is sent to the camera to start individual timers associated with each of the pixels. Every pixel has its own individual timer. When a photon arrives at a pixel on the camera, the timer for that pixel is stopped and the time of arrival is recorded. After many pulses from the laser, a video of light traveling through air is recorded. The camera lends itself to applications where precise timing information is needed, and one such application is recording the scattered light from objects hidden from view, enabling us to look around corners. There are a variety of potential applications for this, ranging from search and rescue missions, where faint signals will enable trapped people to be found, to medical imaging inside the body, where new forms of endoscopy are enabled by time-of-flight imaging. The team at Glasgow University is taking a different approach to imaging and looking into taking pictures outside of the visible spectrum with only single pixels. Normal cameras use a lens to form an image on a rectangular array of light-sensitive detectors. The signal from each individual detector gives the value of the corresponding pixel in the image. An alternative approach, called computational ghost imaging, instead uses a data projector and a single detector to form an image of the object through a process known as data inversion. The data projector illuminates the object with a sequence of patterns that resemble random crossword puzzles, and a single detector collects all the backscattered light. When more of the white squares of these puzzles overlap with the object, the intensity of the light returning to the single detector is higher. One random pattern and the corresponding detector signal does not give an image of the object, but the object can be deduced from a sequence of different patterns and corresponding detector signals. The number of patterns needed gets higher as the desired resolution increases, but a modern-day projector can display the required number of patterns in only a few seconds. Surprisingly, the images produced in this way contain all the information that can be collected by conventional methods. The contours and shading can be recovered perfectly, and even colour information can be gathered with a set of single pixels. Interestingly, the shadows in the image are not determined by the position of the light source, and rather it is the position of the detector that determines the shadow detail. This ghost imaging technique is certainly strange, but this is more than a clever method for three-dimensional image reconstruction. Normal cameras work well with visible light, but getting images in ultraviolet or infrared can be hard. By contrast, data projectors can work over a whole range of wavelengths, even far removed from the visible spectrum. Perhaps we can use this ghost imaging approach to make camera-like systems working over a much wider range of the electromagnetic spectrum.